Bismillah, Alhamdulillah, wassalatu wassalamu ala Rasulillah. This is section 4.3 again. If you have seen the first part about section 4.3, you would have known by now what is the meaning of increasing and decreasing test. We said we have to find f prime, and when f prime is positive, the function would be increasing. When f prime is negative, the function would be decreasing. And if the function increasing then decreasing, then we have local maximum at f of 4. And if it is decreasing then increasing, we have a local minimum at f of 0. And this is called the first derivative test. Now let us talk about concavity. If the graph of f lies above all of its tangents on an interval, then it is called concave up on that interval. So consider this graph. This is the graph, the blue one. If I ask you to find the tangent at this point, the tangent at this point, the tangent at this point, you will always see that the tangent is actually below the curve. So the curve is above the tangent lines. So this is when we say the curve is concave up. So all of these curves are concave up, okay? These curves are concave up. While concave down is like this. So here, if you draw the tangent line to the curve, you will notice always that they lie below. The curve lies below the tangent lines. Okay, so we call it concave downward. So concave downward would be like this. Anything like this is concave downward. Okay. So now let us try to understand or see whether we understood the meaning of concave up and concave down. Now from here to here, what do you see? The curve is concave down. And we call it CD, okay? So CD means concave down, CU means concave up. From B to C, what do you see? Concave down. From C to D, notice, sorry, from B to C, concave up. From C to D, concave down. From D to E, okay, if this is E, concave up. From E to P, it's also concave up. From P to Q, it is concave down, okay? So I hope you understand the shape of concave up and concave down by now. Now, how to find out whether the graph is concave up on that interval or concave down? Well, the second derivative. If the second derivative is positive, then the curve, the graph of f, is concave upward, like this. If the second derivative is negative on an interval, then the graph of f is concave downwards, like this. Okay, so concavity comes up from the second derivative. From the first derivative, we find out whether f is increasing or decreasing. From the second derivative, we find out whether the graph is concave up or concave down. And if the graph changes concavity, changes from concave up to concave down, or from concave down to concave up, then at that point, which the graph changes or the curve changes concavity, this point P would be called an inflection point of the graph of f. Okay, an inflection point. And we may call it IP. Okay, IP inflection point. So let us see this example, and please be careful here. He said in each part state the x-coordinates of the inflection points of f. Give reasons for your answers. So we need to find the inflection points. A, the curve is the graph of f. Okay, so in part A, this is the graph of f. Well, when do we have inflection points? When the graph changes concavity. This means when f prime is positive and then it becomes negative, or from negative to positive. So the graph changes concavity if double prime changes from positive to negative. All right. We can, this is, since this is the graph of f in this case, so we can look to concavity immediately. Now look here, start from here. The graph is concave what? Down. Up to where? Up to here. Is it? No. In fact, up to here. Because still in this part, the graph is concave down. Good. So in all of this part from here to here, the graph is concave down. And now it starts to concave up. So he wants us to find state, the x coordinates. So the x coordinates here is 3. 3 here, when x is 3, we have an inflection point because the graph of f was concave down and then it's concave up. Up to where? Up to here. And now from here, the graph will be concave down again. So here it's concave up and now it's concave down. So 3 and 5. When x is 3 and 5, 3 and 5 at x equals 3 and 5, we have inflection points. So in this case, there are 2 inflection points of this graph. Well, here in part B, he says, if the curve is the graph of f prime. Oh, so this is not the graph of f anymore. So if it is concave down from here to here, that's f prime, not f. All right. So how to find information about concavity from f prime? Let us think. Now we know that when f double prime is positive, then f is concave up. And when f double prime is negative, f is concave down. Can we find out whether f double prime is positive or negative from the graph of f prime? Okay, this is what we need to think about. So what do we know about f and f prime? We know that if f prime is positive, then f is increasing. And when f prime is negative, then f is decreasing, isn't it? This is the part one. All right. Now, if f prime, the derivative of f, if the derivative of f, what if we have f prime here? Then we will have f double prime here. So actually, if f double prime is positive, then f prime has to be increasing. And if f double prime is negative, then f prime has to be decreasing. And in this case, f would be concave up, and here f is concave down. So do you see the relation? So f is concave up means f double prime is positive, means f prime is increasing. F is concave down means f double prime is negative and f prime is decreasing. And since we have here f prime, so all what we need to find out now whether f prime, the points on which f prime changes from decreasing to increasing. Because if f prime changing from increasing to decreasing or decreasing to increasing, then f changes the concavity and then we have an inflection point. Because inflection points when f changes concavity. So f prime is increasing up to here. And now f prime is decreasing up to here. And now f prime is decreasing up to here. And now f prime is increasing. So the points at which f prime changes from decreasing to increasing or increasing to decreasing are these 3 points. So when x is 2 or 4 or 6, we will have inflection points if this curve is the graph of f prime. I hope you understood the solution. Now, one more step. What if double prime has this curve? So this is the graph of f double prime, not the graph of f or f prime. All right. This will help us too. If concave up, when f double prime is positive, f concave down when f double prime is negative. So f will changes the concavity at the points where f double prime changes from positive to negative or from negative to positive. Oh, so if this is the graph of f, now up to here, from here to here, f double prime is negative, and then f double prime becomes positive up to here. Here it is 0. It continue positive, so there is no change here in the sign of f double prime because it's still positive up to here, and here f double prime becomes negative again. So before 1 f double prime is negative, after 1 f double prime is positive. So at 1 we will have an inflection point for f. Also before 7 f double prime is positive, after 7 f double prime is negative. So when x is 7 we will have an inflection point for the graph of f. Notice that all of these in the three cases, these are inflection points for f, okay, for the graph of f. But then you can find inflection points for f if f double prime changes from positive to negative, or negative to positive, or f prime changes from increasing to decreasing or decreasing to increasing, or f changes concavity from concave up to concave down or concave down to concave up. Sketch a possible graph of a function f that satisfies the following conditions. Let me try to sketch the graph of this function, and we can look to the conditions and start by any one of them. Let me start by the first part, okay, because it is the first part. If prime is positive from negative infinity to 1. So if this is 1, so f double prime is positive from negative infinity to 1. So it's increasing. If a prime is positive, so f is increasing. At 1, we can say that f prime is positive, so f is increasing. Okay, f is increasing. Good. From 1 to infinity, f is decreasing. So I can just draw it like this. This graph would be fine because to the left of 1, it is increasing, and to the right of 1, f is decreasing. Good. Now look to part B. F double prime from negative infinity to negative 2. Okay, so I have negative 2 now. If this is negative 2 and this is 2, if double prime is positive, all right, so up to negative 2, the function is concave. If double prime is positive, so the function is concave up. So from negative infinity to 2, the function is concave up like this. Okay, and from 2 to infinity also concave up. So from here it's concave up like this, concave up. And if double prime is less than 0 from negative 2 to 2, so it's concave down from here to here. So let me cancel the first graph now. So this graph will work for both I and double I because it's increasing up to 1, decreasing after 1. And concavity now up to negative 2 concave up, from negative 2 to 2 concave down, from 2 concave up. Limit when x approaches negative infinity. Okay, if we go to negative infinity, why go to negative 2? All right, so negative 2 is what is a horizontal asymptote of this function. So the curve is approaching negative 2. So the line y equals to negative 2 is a horizontal asymptote. So the graph would be like this. And when x approaches infinity to this side, x goes to this side, f of x approaches 0. Okay, so the line x equals to 0 is also a horizontal asymptote. So the graph is like this. Okay, so here y equals to 0 is a horizontal asymptote. So this is what we find out from double triple I. Uh, you remember the definition of the horizontal asymptote. How do you find the horizontal asymptote? You find the limit when x approaches infinity or negative infinity. If the answer is a number, then y equals to -2 is a horizontal asymptote, and y equals to 0 is a horizontal asymptote. So now this graph satisfies all the conditions of, uh, let me graph this concave down, okay? All of this concave down. Yeah. Another question, use the given graph of f to find the following. The open intervals on which f is increasing. All right. Now this is the graph of f. So this is f of x. Increasing. From where it's increasing? Here it's decreasing. Here it's increasing. From where? From 1 to what? To 3. From 1 to 3, the function is increasing. Then from 3 to 4, it is decreasing. Then from 4 to 6, okay, it's increasing. So union 4 to 6. In these two intervals, the function is increasing. Decreasing, we said decreasing from 0 to 1. You write the x, the coordinate here on the x-axis. Okay, from 0 to 1 on the x-axis, the function is decreasing. From 3 to 4 on the x-axis, the graph is going down from 3 to 4. Okay, this is how we find the intervals of increase and decrease. Concave up. Well, it is concave up to here. Concave up from 0 to 2. And from 2 to 4, it's concave down. And then from 4 to 6, it's also concave down. So it's concave up only from 0 to 2. The coordinates of the points of inflection. Concavity changes where? At 2. So the point 2 and 3 is an inflection point, and there is no change of concavity otherwise. So the point 2 and 3. Pay attention that this is a point, okay, while these are intervals. Those are intervals. Okay, question 17. What is the question? Find the intervals on which f is concave up or concave down. And yeah, and find the inflection points. All right. What do we need to do? F prime is okay. No, we need f double prime. So let us start by finding f prime. And then find f double prime. And now we need to determine the signs of f double prime. And to do that, we have seen that we need to find the zeros. So there is only one zero, which is x1. So this is the zero of f double prime. So if you want to find the signs of f double prime, test the intervals from negative infinity to infinity and 1 between. So this is f double prime and this is f. There is only one zero of f double prime. Now we need to know the signs of f double prime. So I want to check, take a number to the right of 1, put it here. Then f double prime would be positive 2. Okay, take a number to the left of 1, 0 for example, f double prime is negative. So here the graph is concave down. Here the graph of f is concave up. So f is concave up on 1 to infinity, and f is concave down on negative infinity to 1. And the inflection point is 1 and f of 1. So it is 1 and you go to f and replace x by 1. So 1 minus 3 minus 9 plus 4, and that's negative 7. So 1 and negative 7 is the inflection point. Another question, same. We need to find intervals of concave up, concave down, and inflection points. So let us find f prime. Well, the derivative of ln is 1 over what is inside ln u times the derivative of x squared plus 5, which is 2x. So this is f prime. Now to find f double prime, I need to use the quotient rule. Derivative of numerator times the denominator minus the derivative of the denominator, which is 2x, times the numerator, which is 2x. So f double prime is equal to, we need to simplify, 2x squared plus 2 times 5 minus 4x squared. Well, I have negative 2x squared plus 10, combining like terms. That's it. Now notice that I need to find the zeros of f double prime. And to find the zeros, I put negative 2x squared plus 10, the numerator, equals to 0. So 2x squared equals to 10. So x squared is 5, and x is plus or minus square root of 5. So these are the zeros of f prime, of f double prime, sorry. Now notice that x squared plus 5 has no real zeros, and it is always positive. So if we need to make a table for f double prime to find the concavity intervals, so this is negative infinity, this is negative square root of 5, this is square root of 5, and this is infinity. Notice that what controls the signs of f double prime is negative 2x squared plus 10, because the denominator is always positive. And notice that the coefficient of x squared is negative. If you listened to the first part, we said when the coefficient of x squared is negative between the two roots, the sign would be positive. And here we have negative. And of course, you can replace x by 0. You will find it's 10 positive. So you can just do it by replacing, choosing points here and substituting in f double prime. So here f is concave down, concave up, concave down, and I'll have two inflection points, negative square root of 5 and f of negative square root of 5, and the square root of 5 and f of square root of 5. So f of square root of 5 and f of negative square root of 5. So square root of 5 square will be 5. So this is in fact ln 10, and also this would be 5. So this is ln 10. So these are the two inflection points. Another question, we need to find f prime. We will use the quotient rule. Derivative of ex is ex. Derivative of ex plus 2 is also ex. So notice that I can take ex as a common factor. So I'll have ex plus 2 minus ex. Notice that ex cancels with negative ex, and the first derivative would be 2ex over ex plus 2 to the power 2. Of course, you have to simplify f prime before you try to find f double prime. Now again, I will use the quotient rule. Derivative of the numerator is 2ex times the denominator. Now, the numerator times the derivative of the denominator, which is 2 times ex plus 2 times the derivative of ex plus 2, which is ex. And now to simplify f double prime, you take common factors. 2 is here and here. Ex also is here and here. And ex plus 2, we have ex plus 2 to the power 1 and to the power 2, we take the smallest power. And now look to the first term, 2ex plus 2 to the power 2, we took everything except ex plus 2 because it's power 2 here. And minus 2ex have been taken, ex plus 2 also, so we still have 2ex. Over ex plus 2 to the power 4. Well, I have 2ex. Ex plus 2 will be cancelled with one of the 4 ex plus 2 below, and I'll have ex plus 2 to the power 3. And now I have ex minus 2ex is negative ex plus 2. All right. So now this is f double prime. The denominator cannot be 0 because ex is always positive. Ex is always positive. The only 0 for f double prime would occur when 2 or negative ex plus 2 is 0. For this, we have 2 equals ex. Applying len to both sides, len 2 would be len ex, which is x. So x equals to len 2 is the 0. This is the 0 of f double prime. Let us make the table here. So there is only one 0 of f double prime. If I choose a number greater than len 2, well, you can find len 2 by the calculator. It's a small number, about 0.7. So if you choose 1 or any number greater than len 2 or less than len 2, for example, 0. If you choose 0, negative 1 plus 2, it would be positive here. But if you choose a number greater than len 2, for example, 10, then negative e to the power 10 is negative, plus 2 it's negative. So if here is concave up, if here is concave down, and I have an inflection point, if is concave up, let us find the intervals of concave up from negative infinity to len 2, and if is concave down from len 2 to infinity. We should have also right here concave up and concave down, where it's concave up here from negative square root of 5 to square root of 5, and it's concave down from negative infinity to negative square root of 5, union square root of 5 to infinity. And we have one inflection point here, which is len 2 and f of len 2. And if you put x equals to len 2, e to the power len 2 is 2 over e to the power len 2 is 2, 2 plus 2 is 4. So it's 2 over 4, or actually half. So this is the inflection point of this function. Now, in these questions, we need to find the intervals on which f is increasing or decreasing, and the local maximum and minimum, and the intervals of concavity. We have some questions, okay? So we will postpone them. We will solve them in another video. So this video is specially for concavity test.